So now let's look at a laser or LED writing for the maskless lithography and the 3D printing using stereo lithography. So first, so why we want to go to maskless? So this is because for the production, for the IC manufacturing, a theoretical mask costs about $10 million. But this is for the manufacturing. For research, we can have the mask with lower resolution, for example, 1 micrometer resolution. For this resolution, the mask can be made by the laser beam writing with the cost about, here said, $400 per mask. But if you are the academic user, you can get some discount. For instance, if you go to the University Alberta clean room, they can make the mask with 1 micrometer resolution for $200. So anyway, to make a mask is time consuming and it is not so cheap. So the most straightforward method to use to the laser lithography is to use the focused laser beam. So when you have the focused laser beam focused to say sub-micrometer resolution, we can write the resist pixel by pixel. But the problem, because it is written pixel by pixel, it is a very slow process. It's very slow. So yes, it's still much faster than electron beam lithography. So to increase the throughput, to make the exposure faster, so we can expose the resist block by block or field by field by projecting 2D image onto each block area of the resist. So as you can see here, so we can expose this block, then we expose the next block, then we expose next block. This will be faster than if you expose pixel by pixel using a focused laser beam. Or we can expose the resist strap by strap. So in this case, so this is like a one strap. So the stage move continuously, not like a step by step. So the stage move continuously. So each of the pixels will be exposed by many of the mirrors. So here we have the digital mirror device by many of the mirrors. For example, if this device has a 1024 by 768 mirrors, tiny mirrors, then each of the pixel will be exposed by 768 times. So this one is 1024 pixel, this is 768. So each pixel will be exposed by 768. This is called a strap by strap. The advantage for this method compared to the field is that, so because the stage move continuously along the strap direction, there is no boundary. There will be no boundary. So when there is no boundary, there will be no staging area. But still, there may be some staging area along this direction. So here, let's look at how to do the maskless aligner, maskless lithography. So first, so the sample, as you see, it sits on the stage. Let's move in the XY direction. So there is no set stage, so the rotation can be done digitally. It can perform autofocus by using a laser beam. So this lens cannot be used for the autofocus. There will be another laser beam nearby to do the autofocus. Another way to do the autofocus that is also used for the commercial production is to use the thermal. For example, if you have something hot on the surface, so how fast the heat gets dissipated to the surface depends on how far away that surface is from the wafer surface. This way, by detecting the temperature of that surface, you know how far it is from that surface to the wafer surface. So this is called a thermal focusing. But normally we use the laser beam focusing. So the pattern design is loaded digitally into the DMD. So this one is called spatial light modulator. So usually it is the DMD device, which is called digital mirror device. So we will see the DMD device in the next slide. Basically, so we have the pattern design, then we load the pattern into this DMD. After this DMD, here we have the image we want. Then we transfer the image, focus the image onto the wafer. So we have the light source, illuminate the DMD, and go to the wafer to form the image. So the exposure field gets snapped across the entire wafer. So this corresponds to the case of the block by block exposure. So the staging can be smoothed out by overlapping the exposure field. As I said, if we go continuously this direction, then there will be no staging area along this direction. But there will be staging area along this direction. So between this stripe and this strap, there may be some overlap or there may be some gap. So this is called a stitching error. So to minimize the stitching error, so what we can do? So we can do some intentionally we do some overlap. But when we do the overlap, that means the overlap region, for example, this is the overlap region. So we expose this overlap region, half of those by when we expose this strap. Then we expose another half of those when we expose the next strap. So this way, the boundary will be kind of blurred. So the exposure of those is determined by the on time over the DMD. So how long it turn on the DMD and also how high is the power of the laser determines the exposure of those. So it is possible to do the grayscale lithography. If you remember, the grayscale lithography is used to make the 3D structures. A different area they are exposed at different doses. If for the case of the negative dose, the higher dose give you taller height, lower dose give you smaller height. So this is the grayscale lithography. That means normally, for the conventional lithography, it is kind of black and white. So we have constant dose. So grayscale means we have varying dose at different positions. But this grayscale lithography is not so convenient as the electron beam lithography because the dwell time, the on time is fixed. So for each scan, the on time is fixed for this kind of setup. But you can still do the grayscale lithography by doing multiple scans. For example, you scan at one time, you expose some area, then you scan another time, you expose another area. This way, the dose at different area will be different. Then in the end, after development, you get different pattern height. So this is the idea of grayscale lithography. And now let's compare the normal optical lithography with the maskless lithography. In the lab, some people call it as aligner. For the mask aligner, this usually we refer to the proximity lithography or contact lithography, but not projection lithography. This is the maskless aligner. So this one is used for the lab. This one is also used mostly for the lab, but it is also used for the production. Production without very high resolution. For example, it is very nice to be used for the printer circuit board. So for the mask aligner, it is the pattern replicator. So we copy the pattern from the photo mask onto the photoresist. So this one is the pattern generator. So we generated the pattern on the photoresist without using a mask. Here we need a physical mask. Here we need only the pattern design. Takes a long time to change. If you change the design, you need to make a new photo mask. But here we can change the design any time. It's very fast. The mask can be contaminated or damaged. So here we do not need any mask. There is no such issue. But still, the main advantage for the mask aligner is because we copy the pattern. So the pattern of the entire photo mask is copied at the same time. So usually, the exposure time takes about a few seconds. But when we do the maskless aligner, so we do it, even though we do it strap by strap or block by block by block, it takes a long time. For instance, the exposure rate is 1 to a few square centimeters per minute. For a full 4-inch wafer, the 4-inch wafer is about 82 centimeters square. It will take about 1 hour. This one takes about 1 hour for the exposure, but this one takes about a few seconds. So, but this one, because it is very convenient, it's so convenient, you do not need to make the photo mask every time. As a result, so when the University of Waterloo, the quantum nanofab in the QNC building, so we have this one about 2 years ago. So quickly, so most students, they left this mask aligner and go to use this MLA 150 from Heidelberg. And today, so this machine is among the busiest equipment in the lab. So it is very popular, very useful for research. But for production, you care about the throughput. So this one is still better for your mass production. So now let's look at the digital mirror device. So this is this part is the digital mirror device. So this is the key for this maskless aligner. So what is the digital mirror device? So this is the MEMS device. MEMS, you can see here is like a MEMS, micro electromechanical system. It is fabricated by the MEMS fabrication technique. So it is also called a DLP, a digital light processor. So the company TI they call it as DRP, but it's also it's also very called as DMD. So in the DMD device, there are thousands or millions of mirrors on a tiny chip. There you can make many of the mirrors. Each of the mirror here is about 10 micrometer. So 10 micrometer. So you can make so many of them. So each of the mirror can be independently controlled. So we have on and off state. So what is on and off state? For instance, if this is the lamp, this is the light, the light source shine on the DMD. For this mirror is turned this way, so the light comes to the projection lens. So this is the on state. So for this mirror, the light coming in is reflected to the light absorber. This is the off state. You can also see here the bend of the mirrors determines whether the light goes to form image or the light gets lost. So the mirror size is about 10 micrometer. So the material on the top is aluminum, because we need something. It's a mirror, so we need something very high reflection. So very pure aluminum film, the metal film gives the very high reflection. So the layer below it, I think, can be a silicon nitride, low stress silicon nitride, but I'm not so sure what exactly the material is below the aluminum coating. So this is DMD is mostly used for the projector. This is the projector from the company called Christie Digital. Somebody may be aware that there is a Christie Digital in the Kitchener, in the Waterloo region. So in the past few years, this is not a small company. They have about, I think, 1,000 people working in this Waterloo site of the Christie Digital. But recently, I think they have laid off some people. So how the projector worked? So here's the idea of the projector. So first, so you have the light source. This can be LED, light emitting diode. Then you have the lens. And you have the color filter, because we want color. So we have the color filter. So then we have the shaping lens. Then it goes to the DMD. This is the mirror device. So after DMD, the light is reflected back. Some pixel we have the light come back. Some other pixel the light get lost. Then we have the lens and get projected onto the screen. So this is the idea of the DMD. For the case of the lithography, is similar. It is a similar setup. So here the drawing is just, as you can see, is just a schematic. So the laser light, the LED or laser light should come from here. LED or laser should come from here. It should come from here, then reflected, then come to form the image. Not, it cannot go through the back, from the back over the DMD. Should it come from the front, then reflect it. Yeah, so this is the mirror device. So now let's look at another 3D printing. So I didn't cover this topic for some years, but because I know that the 3D printing is becoming a very, very hot topic recently, so I added back the slide. I'm sure you have taken the 3D printing course for the first year. You have learned SolidWorks and the 3D printing. So the University of Waterloo, we have bought a few 3D printing equipment. So we bought 3 for the NE, for the nanotechnology and engineering lab, and those 3D printers is donated by the AE alumni. So the idea, as you may have known, if we want to make this device, it's called microclip. So what do we do? First, we slice it. We have many layers. So we create a digital file of about more than 5 micrometer thickness slices of the drawing. Then we expose the pattern layer by layer. We expose it layer by layer. For example, for this layer, this slice, the pattern will be like this. So we will expose this pattern for this particular layer. So the resist is UV curable liquid resist. So the resist will be cross-linked or solidified by the UV light. So the resolution for this process, normally for the XY plane, is about a few micrometer. For the Z direction, it is the slice thickness, which is normally higher than 5 micrometer resolution. So how thick is the slice? how thick should be the slice. So the slice, the thickness should match the UV light penetration depth of the resist. For example, if the slice is too thick, then only the top part gets exposed. The bottom part of the slice will not be exposed because the light gets absorbed by the top part. If the slice is too thin, then the UV light will penetrate through the slice and to expose the layer below it. That means the previous layer will also be exposed if the slice is too thin, thinner than the light penetration. Another consideration is the printing speed. So this is very important because the printing of such thing may take many hours. So obviously, the higher the resolution, the slower the printing speed. Here's the schematic showing how to do the stereo lithography. So for the stereo lithography, so we have the resin, so we have a beaker, so we have a container that has the liquid resin. So we put the sample, onto the support. Then on the wafer surface, the resist will be exposed. Then we lower it. So we lower the support. Then a new layer of the resist will cover the surface. Then it gets exposed. Then we lower it again. Then another layer will cover the surface, get exposed. So this is how you build the image, how you build the part layer by layer. So here again, we have this image forming array. This image forming array for the commercial product, this one is also DMD. So it is similar to here. So this here is called spatial light modulator. Here is called image forming array. So this is also DMD. But because we know the DMD is reflection, is the mirror, is the mirror. So we need to do the reflection. That means the light should not come from the backside of the DMD. So instead, the light should come from here, come to the DMD, then get reflected. So this is the DMD. So the light should come from here, get reflected. Another point is that this mirror here looks like the image is far away from the mirror. So in reality, they should be very close. So I think sometimes we even do not need to use the mirror. If we put this thing right on top, they have smaller working distance. So as you know, the farther away from the image, so the farther away the distance from here to here, the lower will be the resolution. To get just a few micrometer resolution, so I think that the lens should be quite close to the wafer surface, quite close to the resist surface. In this case, we may not use this mirror. We don't have to use the mirror. So because it takes time, it's very time consuming. It is very time consuming to form a new layer of the liquid resist on top of the existing pattern. So we shouldn't have too many layers. As a result, so normally this is good for the structures whose height is much less than the lateral size. If the height is not very high, then we have fewer layers. Then the exposure time will be shorter. So this is the typical setup. So we can also export from the bottom set. If we export from the bottom set, then the part will move upward. So each time the part will move upward. This one move upward. So this one it move downward. The idea is the same. So those are examples of this is the 3 millimeter tall structures, which 53 micrometer layers. If we look carefully, so you can see the layer by layer structure. So this one is diameter 2 millimeter diameter resist pattern. So this one is the scale bar here is 20 micrometer. So the resolution here I would say roughly 10 micrometer resolution. So this one, so the scale bar is 100 micrometer. So the resolution may be about 10 micrometer. So those are the examples of the stereo lithography. Now I'm sure you know about the 3D printer in the AE lab or in the E5 building, engineering 5 building. For that kind of 3D printing, it is very fast. You can print a big part, but the resolution is very poor. But that kind of 3D printing is based on. For the 3D printing in the engineering 5 or in the AE lab, that is not very high resolution. So that one they use nozzles. They use some nozzles, so they squeeze the liquid resist. They squeeze the liquid resist they squeeze the polymer through the nozzles. So the polymer gets melted at the end of the nozzle. Then it's squeezed out. Then it is goes to the surface. Then it is cooled down by the blowing fan. Then this way you build layer by layer. But this kind of 3D printer, even though it is very cheap, the resolution is not very good. For instance, the 3D printer in the engineering 5, the resolution I have used it, the resolution is about 200 micrometer, about 200 micrometer. But this kind of 3D printing, the resolution, as you can see here, this one is 20 micrometer. Sorry, this one is 10 micrometer. So you can get a few micrometer resolution. But of course, the printing speed is also should be much slower than the printing speed of the cheap 3D printer in the campus. And now let's look at another 3D. This is also 3D printing process. It's 2-photon lithography. So the difference. So this one give you the resolution about a few micrometer. So this one you get resolution on the order of 100 nanometer. Here is the idea of the 2-photon lithography. So you have the pulse, the laser. So you have the laser pulse. So the laser pulse has a wavelength 800 nanometer. So we know that 800 nanometer, the photon energy is not high enough. So this is not enough to expose the monomer resist. So then we have this lens. So the light is focused onto the resist, inside the resist. At the focal point, 2 photons can be absorbed. 2 photons can be absorbed at the same time. So when the 2 photons is absorbed at the same time, so effectively 1 photon is 800 nanometer. So 2 photons effectively we have a 400 nanometer light get absorbed by the liquid resist. But this is the UV light. But this is useful to expose, to cure or cross-link the monomer liquid resist. But this is the idea of the 2-photon absorption. But this is the physics of the 2-photon absorption. For the normal 1-photon absorption, so we have the light coming in, the electron jump from the ground level to high energy state, then relax to the E2, then go to the ground level again with the emission of the lambda 3. So this is the typical luminescence process. So the luminescence can be a fluorescence or phosphorescence. For the case of the phosphorescence, the emission will take some delay. But for the fluorescence, the lambda 3 is emitted right away, no delay. So for the 1-photon absorption is proportional to the intensity of the light. For the 2-photon absorption, so the absorption energy, absorbed energy is proportional to the square of the light intensity. So here, as you see again, so we have 2 photons get absorbed at the same time. Each of them has lower energy, but 2 photons is energy high enough. So the electron jump from the ground state to the high energy state, then relax again, and then go to the ground state with emission of the lambda 3. So why we need 2-photon absorption for the 3D printing? So here you can see the idea. So the top part, this is the 1 photon with 400 nanometer wavelength. So as you can see, along the path, there is absorption all along the path of the light. So this way, we do not have well-confined absorption, so the pattern will be blurred. So the lower part, the lower beam has this one is 800 nanometer. But this is very strong light intensity. So there will be 2-photon absorption. So the 2-photon absorption, only this part, only at the focal spot, the 2-photon absorption will happen. As a result, only this part we have the exposure of the resist. Along the path, we have the negligible exposure. So because the region, first, the light here intensity is lower. Secondly, the wavelength is 800 nanometer. 800 nanometer, as you can imagine, higher energy has lower absorption. And also longer wavelengths have lower absorption, and also longer wavelengths has lower scattering by the liquid. So here is the 2-photon excitation event. So this happened within 10 to minus 18 seconds. So this is really a quantum. It's really like a quantized event. So this time is very short. If you calculate lambda over c, some people may think this is the a characteristic time of the photon of the light. So the light wavelength divided by the speed of light. But this one gives you about 10 to minus 15. Give you 10 to minus 15 seconds for this a few hundred nanometer wavelength and the speed of the light. So 10 to minus 15. But for the two photon absorption, it happened within 10 to the power 18 minus 18 seconds. So the absorption is proportional to the square of the light intensity, as you see it here, to the square of the light intensity. So for this to happen, the photon density has to be close to 1 million times required for the one photon absorption. So only the focal point of most locked pulsed laser. This is the femtosecond laser. This is the femto 10 to minus 15. So this femtosecond means 10 to minus 15 second pulsed laser has this high photon density. So how high density you need? So one way you can think about this is like this. You have one photon here, you have another photon here. So the distance between the two photons, should be comparable to the lambda, comparable to the wavelength. This way, the two photons can be absorbed at the same time. So we have this high density of the photons. This gives you very high power for the photon. So you will do the calculation at one of the assignment questions. So here is the example of the 2D structures made by the two-photon lithography. So first, how to make those 2D structures? So the idea is similar to this one. The idea is similar to here. So you have the liquid resist. So here I use the beaker, but very often, because the height, the sample is very short by two-photon lithography, so we use a wafer. So we put a drop of the liquid resist onto the wafer. Then we have this lens immersed inside the resist. That means the two-photon lithography is kind of immersion lithography. So why we need immersion lithography? Because otherwise, if the lens is in the air, then at the air liquid resist interface, there will be some scattering. So the resolution will not be very high. For the two-photon lithography, we talk about 100 nanometer resolution. So we have to immerse the lens inside the liquid resist. This way, we get better resolution. So then you move the wafer along the X and the Y and the Z direction. Then only the focal point gets exposed. Then you get the 3D structure as you want, as you see here. So this is the change. The feature size here is 120 nanometer. This is the human body. This one is the most famous two-photon lithography example. This is the bull. So the size, I don't remember how big. I think the scale bar here may be 1 micrometer a scale bar. This is published by the Japanese group in Nature about 20 years ago. So here is the slide. So now I can show you some other 3D printing technique. So the first one is called laser metal melting lithography. So here we see the limit for this lithography and for this lithography. The material we made is the polymer resist. So you can put some metal nanoparticles inside. If you put, for example, magnetic nanoparticles, if you mix magnetic nanoparticles into this liquid resist, in the end you can make the structure magnetic. But still, the bulk of the material is polymer. We know the polymer is only good for a kind of model, but it is not good for tools or for molding. The mechanical strength is not high enough. To solve this problem, we need to make some metal structure like this. So how to make metal 3D printing? So I will show you a video on how to make metal 3D printing.
Direct metal laser sintering, also known as DMLS, is an additive manufacturing technology that creates metal parts directly from 3D CAD data without the need for tooling. DMLS utilizes a variety of metal and alloy materials, such as stainless steel, cobalt chrome, and Inconel, to create strong, durable parts and prototypes. DMLS is an excellent choice for functional metal prototypes. high-temperature applications, and end-use parts. The DMLS process begins in the same fashion as other layer additive manufacturing technologies. A program takes 3D CAD data and mathematically slices it into 2D cross-sections. Each of these sections will act as a blueprint, telling the DMLS machine exactly where to sinter the metal material. The data is then transferred to the DMLS equipment. A recoater assembly pushes powdered metal material from the powder supply to create a uniform layer over the base plate. A laser then draws a 2D cross-section on the surface of the build material, heating and fusing the material. Once a single layer is complete, the base plate is lowered just enough to make room for the next layer. More material is raised from the cartridge and recoated evenly on the previously sintered layer. The DMLS machine continues to sinter layer upon layer, building from the bottom up. As the part is built, support structures are added to give supplemental strength, define features, and overhanging surfaces. The completed part is then removed from the base plate and treated with an age-hardening heat process to further harden the part. Any support structures are
this process is called the direct laser melting sintering. And now we will look at another a small part, a very small part that is magnetic. So it can swim in the liquid. So the purpose for this one can be, for example, for the drug delivery. So as you will see, it can pick up nanoparticles, then it can be released at the spot we want. So this small part, magnetic part, is controlled by the magnetic field, so it can swim in the liquid. So this part is made by the rotating part is made by the 2-photon lithography with magnetic nanoparticles embedded into it. So it is magnetic. So next, you will see a 2-photon lithography process. So the sample it moves around. So the laser beam is fixed to the same spot. The sample the waveform move along the X, Y, and Z direction to do the 2-photon exposure. So now we will see another video for the 2-photon lithography. This one is from the Nanoscrap. Nanoscrap is the German company that made the 2-photon lithography equipment.